Hi everyone, this is a quick video about L'Hopital's rule. So L'Hopital's rule is useful when we are finding the limits of indeterminate forms. Indeterminate forms are forms of limit problems where you have the limit of a fraction, basically a function fraction like that. And if the limit is going to 0 on top and bottom, or going to infinity on top and bottom, then basically we don't know what the overall limit is, because that's what we mean by indeterminate. The overall limit might turn out to be a number, or it could turn out to be 0, or it could turn out to be infinity, or it could turn out to be DNE, right? It's indeterminate, because really what's happening is that we have a race between two functions, either that are both growing or that are both getting smaller and smaller, and the final answer is going to depend on which function kind of wins the race, right? So if I have an example like the limit as x goes to, let's see, which one do I want to do? X goes to infinity, for example, of ln x over x minus 1, right? So if we think about this this overall limit here, the limit means what does this ratio of the two functions do as x gets bigger and bigger, right? So the top is going to grow, because we know that ln x is a graph that looks like this, and it grows as x goes to infinity. Y goes to infinity too, right? So that's infinity, and on the bottom we know that the limit of x minus 1, well, x minus 1 is just a straight line, right? With slope, actually it would be slope 1, intercept minus 1, so it will be something like that, right? So both of these functions are going to infinity. Both of them are growing as x grows. The question is, if we do a division like this, which one is going to win? What's going to be the final answer? And that could be anything. And L'Hopital's rule is going to help us find that. So L'Hopital's rule works like this. Like for that problem here, I would say the limit of the top goes to infinity, the limit of the bottom goes to infinity. Therefore, this entire limit here, which I'm trying to find, is an indeterminate form of type infinity over infinity, and then I would apply L'Hopital's rule. And L'Hopital's rule says that I can just, instead of doing that limit, I can do the limit as x goes to infinity of 1 over x, which is the derivative of the top, divided by 1, which is the derivative of the bottom. Now this is very clearly equal to 0, right? Because if the bottom is growing and the top is just 1, then this answer is 0, right? So that means that my original limit is also 0. So that's L'Hopital's rule. Okay, so let's do a few of the homework problems. I want to do number 2, which was in the true and false, right? Because that's an even problem, so I want to give you the answer. Number 2 said L'Hopital's rule can be applied to evaluate any limit of the form limit of f of x as over g of x as x goes to a, and that would be false, because it can only be used if the limit is an indeterminate form of type 0 over 0 or infinity over infinity. Actually, there are other indeterminate forms as well, but for our course, this would be our answer. Let's take a look at number 11. So for number 11, we're given these two graphs, right? So we've got a function, and it looks kind of like this. And then we have another function. Well, we're given the tangent line to this function at the origin, and that looks like that. And this is given to be y equals x, and this function here is just called y equals f of x. So then the question says, what is the value of the limit? So we're looking for the limit f of x as x goes to 0, f of x divided by e to the x minus 1, right? And first off, let's just say L'Hopital's rule is going to be useful only when we're looking at the limit of a ratio like that, one function divided by another function. Okay, so let's check what happens to the top. So the limit of the top, it's a graphical problem, right, in the sense we have the graph of f of x, and you can see that as x approaches 0, f of x approaches 0, right? The bottom is an equation, so there we can plug in 0 and get e to the 0 minus 1, e to the 0 is 1, so 1 minus 1 is 0, right? So this is a limit of indeterminate form. This limit is an indeterminate form of type 0 over 0, and we are justified in applying L'Hopital's rule. To apply L'Hopital's rule, we simply say that this limit is equal to the limit of f prime of x over e to the x, because that's the derivative of the top and the derivative of the bottom separately. Do not do the quotient rule for L'Hopital's rule. Okay, so now now to do this limit, we're just back to unit 1, and we have to put the 0 into the top and to the bottom, and the bottom is easy. That just comes out to be e to the 0 or 1. The top, we have to remember that since f, it goes back to continuity. Since f is continuous, f prime is continuous. If f prime is continuous, then the limit at an arrow number is equal to the function value at the arrow number. So I can say that that limit is equal to f prime of 0. F prime of 0 means the slope of the tangent line to f at x equals 0. The tangent line is drawn in green, right? And it's the slope of the tangent line is 1. So that means that f prime of 0 is also equal to 1. 1 divided by 1 is equal to 1 for our final answer. Okay, let's try to do some problems like, let me see, maybe number 27 would be a good one to try. The limit as x goes to infinity of ln rad x divided by x squared, right? So to write this properly, always showing what happens to the top separately and what happens to the bottom separately, right? So this bottom clearly goes to infinity. The top also, it's ln of the square root of infinity. Infinity is not a number. Square root of infinity just means a bigger and bigger number. Ln of a bigger and bigger number is bigger and bigger, so that one's infinity too. So we do have an indeterminate form of type infinity over infinity, so L'Hopital applies. And then we can actually write that down and then come up at the top and just apply L'Hopital's rule to say that this limit would be equal to the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom, if that exists. So ln rad x is a chain rule, so I have to do 1 over rad x, that's out prime of n, times the derivative of the inside. So that all comes out to, I think, 1 over 2x on the top and 2x on the bottom. So keep change flip gives me 1 over 4x squared. Now, if x is going to infinity, 1 over 4x squared is going to 0. Okay, let's do 29. 29 goes like this. Some of this is just being good at taking derivatives, right? Because that's what the rule does. It takes the derivative of the top and the bottom. So this one, 8t minus 5, 8 to the t minus 5 to the t over t. Well, same gig every time. The limit, check the limit of the top and the bottom. I mean, it might not work out, but we're going to check it. 8 to the 0 minus 5 to the 0, that's 1 minus 1 or 0. Bottom is 0. So it is a candidate for L'Hopital's rule. Indeterminate form of type 0 over 0. L'Hopital applies. And then we go ahead and apply it. You can apply it up here. So this is going to be equal to the limit. Arrow number stays the same. Take the derivative of the top, right? Derivative of the top, good review moment, is equal to 8t, sorry, messed up there, 8 to the t ln 8 minus 5 to the t ln 5, right? And then derivative of the bottom is 1. So then I try to put the arrow number and see if I get a meaningful answer out. I get 8 to the 0, which is 1. So ln 8 minus 5 to the 0, which is 1. So ln 5. And now remember that the log of a difference is equal to the log of, that. ln 8 minus ln 5 equals ln 8 over 5. Okay, so last one here I'm going to do is number 31. Number 31, if I recall right, is a couple times, L'Hopital's rule can be applied as many times as you need to, so long as you get an indeterminate form each time before you apply, right? So let's check this one out. The top is going to infinity. The bottom is going to infinity. So it is an indeterminate form, type infinity over infinity. L'Hopital applies, and I can go ahead and apply it. So when you apply L'Hopital, this is equal to the limit as u goes to infinity. Derivative of the top is 1 over 10 eu to the 10. And derivative of the bottom is 3u squared. Okay, now this is what happens. The top is still going to infinity. 1/10 of infinity is still infinity. The bottom is still going to infinity. And so I will apply, I won't write the verbiage here, but you should write the same verbiage about how this is type infinity over infinity, and we're justified in applying L'Hopital's rule. Now you got 1 over 100 eu to the 10, right? Because I'm doing the chain rule on, let me just explain that so it's not confusing. E to the u over 10, right? The inside function is u over 10. So in prime is 1/10, right? U over 10 just means 1/10 u. And the outside function is e to the x, so the out prime is e to the x. So out prime of in times in prime, right, gives me that. That would be the derivative. Okay, so that's what I've been doing up here. Anyway, this guy is again, believe it or not, infinity over infinity. So we'll write that one last time, u, not x. Trying to write fast here. Okay, so again, indeterminate form, same verbiage, and L'Hopital applies. And I think this is the last time, because you can see, if you have this like u cubed in the bottom's going to keep on being infinity until you get it down to a number, right? So in this case, now I get 1 over 1,000 e to the u to the 10 over 6. And so finally, my top now is going to infinity and my bottom is going to 6. So this can be clearly said to be infinity, right? So now you could argue that, one might look at this initial problem and realize that an exponential is going to grow faster than a polynomial. And so you could kind of predict that that was going to go to infinity anyway. But L'Hopital's rule gives us a more, just a firmer way to prove that.